Look around any city. The overwhelming majority of the structures you see, apartments, offices, parking garages, hospitals, are made from one material, reinforced concrete. It's so ubiquitous we take it for granted, but the idea behind it is an engineering masterstroke of simplicity and efficiency. It solves the most fundamental problem in construction materials. Concrete is incredibly strong in compression but weak in tension. Like stone, steel is incredibly strong in tension. Reinforced concrete is the marriage of these two, creating a composite material where each does what it does best. But this marriage only works if you understand the rules of the relationship. Let's break down how this composite actually behaves under load. The core principle is composite action. Imagine a simple concrete beam supported at both ends with a load in the middle. When it bends, the top fibers are in compression and the bottom fibers are in tension. Plain concrete would crack and fail at the bottom almost immediately. Now, we place steel reinforcing bars, or rebar, near the bottom. As the concrete cracks, which it will at a microscopic level, the tensile stress is transferred to the steel via bond stress, the grip between the deformed bar surface and the concrete. The steel elongates slightly, resisting the tensile force, while the cracked concrete above continues to resist the compression. They work together as a unit. The beam's moment capacity is now a function of the steel's yield strength and the concrete's compressive strength. A pro tip for detailing: the bars must be anchored properly beyond the point where they are needed, using development length or hooks, so that bond stress can develop without pulling the bar out of failure mode, called bond failure. Now, let's talk about the different members. In a column, the primary load is axial compression. The rebar's job here is not primarily to carry load, but to confine the concrete and provide ductility. Closely spaced ties or spirals wrap the vertical bars, preventing the concrete core from explosively spalling under high load and preventing the vertical bars from buckling. This allows the column to deform and absorb energy in an earthquake without suddenly collapsing. In beams and slabs, we also must resist shear forces, the diagonal tearing stresses. Concrete has some shear capacity, but to prevent sudden, brittle diagonal tension cracks, we add shear reinforcement. This is usually in the form of stirrups, vertical or inclined steel hoops that wrap the longitudinal bars. They act like internal clamps, holding the concrete together and carrying the tensile component of the shear force after the concrete cracks. The most critical zones are the connections, especially beam-column joints. This is where forces are transferred, and in earthquakes, it's the most vulnerable point. The design philosophy is strong column, weak beam. We want any plastic hinges yielding to form in the beam, which are easier to repair, rather than in the columns, whose failure could lead to progressive collapse. This requires careful detailing with closely spaced ties in the joint region to confine the concrete and maintain the bond under reverse cyclic loading. Reinforced concrete is not a perfect material, it's a design system. Its success depends entirely on the detailing. The specified concrete cover protects the steel from corrosion and fire. The bar sizes, spacing, and placement are all calculated to ensure the forces flow smoothly from steel to concrete and back again. A common and catastrophic construction error is misplacing rebar, setting it too low in a slab or beam, which drastically reduces its effective depth and moment capacity. In essence, reinforced concrete is a brilliant, low-cost way to create monolithic, fire-resistant, and moldable structures. The concrete provides mass, shape, and compression. The steel provides the tensile strength and ductility. Together, they form the literal reinforced skeleton of our modern world.